to review the impulse response, and then this is the formula I've written here, okay, which is this one. I told you that I can write any function in terms of the weighted superposition of the time-shifted unit impulse, okay? And this was the sort of a more rigorous mathematical proof of that. So don't, yeah, this one. So don't worry about that. Now this one, so this is the important one, okay? The linear time-invariant system. This was the linearity property that we saw. Okay, this one you've seen. You've seen also the time-invariance property. When you have a linear time-invariant, it has to satisfy both those properties. Okay? It means if I have something like this, scaled version multiplied by x, which is shifted by some time, and it goes from 1 to n. So why was it that I told you the multipath system is linear time invariant? You can see it's very similar to this, right? It's very similar to this. Okay, you have some weight A, and you're shifting it. So it's this is exactly like the same system like that. Exactly. So you basically, the basic idea is if you shift the signals and you multiply them by some constant and you sum them up for the input signals, you should do the same thing to the individual output signals. So these are the individual output signals, these are the individual input signals. And this is the assumptions. Okay? So I assume my linear time invariant system, when this is the input to it, x1, the output is y. When x2, it's y2, and so on. This is the assumption I make. I can make any assumption I make. But then, using this assumption, I want to show that if I can show that the system satisfies this property, the system is linear and time invariant. Okay, so I have to show that the system satisfies this property. And if I show that, the system is linear time invariant. Okay? So, having said that, this is the most important stuff. Okay? Because I think conceptually, this summarizes everything. Okay? Conceptually, this slide summarizes it. Suppose I have a linear time invariant system. Okay? And when I input this signal x of t, okay, my output signal is this signal y of t. Okay? So I give you an input-output relationship, and then I tell you what is the output of this signal. Okay? Which is a periodic version of this x of t. Okay? X of p is a periodic version of this x of t. Okay? Now, what we did here was the following. I said I could write my x of p as a scaled, shifted version of my original signal. Because you can see it. So what is the original signal? It's the value is 1 between -5 and 5, and everywhere else the value is 0, right? So if I take that and multiply it by 2, okay, this gives you this here, right? This one. So if I shift it now by 2 times 1, okay, 2 times 1, it shifts to here, right? Yeah. If I shift it here, the signal is going to be again from 1.5 to 2.5, and the height is going to be 2. Same thing if I shift it by 4 now. Okay, you can see that, and the reason you could do this addition is because each of these individual ones is 1 for this duration and 0 everywhere else. And when you add them together, you get this periodic signal. Okay? So this is very important. So if you don't understand it, ask questions. It's okay. Yeah.
It's periodic, and there's a break of no signal for
exactly.
length 1.
Exactly.
So how is that length 1 when the shifting is of 2?
Because you have a half here and a half here.
Oh,
and the half and a half add up to 1, therefore there is only 1. Exactly.
Yeah.
Okay? Exactly. So, do you want me to go over this a little bit in a step-by-step? Yeah. So this is the general idea. Okay? I have this signal. Okay, I have this signal x of t. Okay, and I want to generate using this x of t this periodic signal. Okay, the way I could do that is that this signal itself, okay, is from 0.5 to 0.5. The magnitude is 1, the original one. Okay, so let's construct first this portion. Okay, first this portion. Okay, what do I have to do? I have to simply multiply this by 2. Okay, that will give me magnitude of 2, exactly. That will give me the magnitude of 2, and it's from 0.5 minus 0.5 to 0.5. And everywhere else, the key is here that everywhere else the value of signal is 0, right? Okay, so now let's construct this part. Okay, so when I want to construct this part, what do I have to do from this? Okay, again I have the same original signal x of t. Okay. Okay, so 0.5, 0.5, the height is 1. First I have to shift it, okay, by how much?
2.
By 2, right? Because if, take the center is at 1. Where is the center here? The center here is at 0, right? The center here is at 0, the center here is at 2, right? So you have to shift it by 2. Is it to the left or to the right?
The right.
Therefore it has to be by minus 2, right?
Yeah.
So this would be shift, okay, by minus 2. Okay, so I shift this by minus 2 and I also multiply by 2. Okay, this is exactly like the multipath system that I told you. Like you shift the signal, you multiply by 2, right? And what happens in the output? On the output, I get a signal that's from 1.5 to 2.5. The center is at 2, right? The magnitude is also 2. And everywhere else is 0. Okay? So what happens when I add these two? When I add these two, the result is equal to this signal. It's from minus 0.5 to 0.5, it's 2. It's 0 between these areas because you can see in this area it's 0, and also in here it's 0. So 0 plus 0 is 0. And here is 1, here is 0. When you add the 2, you get another you get another non-zero value, which is 2 between 1.5 and 2.5. Okay? So if you do this individually for all values of n from minus infinity to infinity, you get your periodic signal. Okay? You get your periodic signal. So did it sink in, or you want me to go over it once? Okay.
What's the part at the bottom?
So I'll talk about that after. Okay? So did this first part sink in? Do we understand what we did to this side? All we did was to write this periodic signal x of p, okay, in terms of the signal x of t.
So the system's taking a periodic signal and converting it to a periodic signal?
No. No. That's not what it is. So I told you when the signal, because it's linear time invariant, okay, what we want to do is we want to write it in terms of the original signal that we know already the output to. Okay? So we know the output of the system for this particular input. So when we have this new input, what we're trying to do is we're trying to reconstruct this new input in terms of the old output, which we know the output to. In terms of the old input, which we know the output to. Okay? And from that we want to get the output of the system when this is the input. Do you get it? Any other questions? Good? Okay? So we've came up to this point. Okay? Now, because the system is linear time invariant, it satisfies this property that if I scale the individual elements of x by 2. On the other side, I have to scale the individual elements of y by 2. Okay? I also have to shift, if I shift by 2m, I have to shift on the other side the individual elements by 2m as well. Okay? By 2m as well. Therefore, I could write the overall output to this new input in terms of this outputs that we knew. Okay, the overall output, did I say input?
No, you said output.
I said output, okay. So the overall output in terms of the ones that we know. Okay, and then we could add them up. The same thing we do with this, we do with that, and this is the output we get. Okay? So make sure you understand this. Okay? I emphasize again, and there's a reason I emphasize. Make sure you understand this. Okay?
So what's,
I forgot
what kind of a question would you pose and what kind of an answer would you
Yeah.
Yeah.
I was just asking, so we can only know the periodic function xp of t because the system, because we are given that the system is linear time invariant.
Exactly.
So if we were told, we were not told if it was linear time invariant.
You couldn't use these properties. You couldn't use any of these properties.
Okay.
I mean, the whole point is that because the system is linear and time invariant, if you write this periodic signal in terms of this input signal that you already know the output to, even though you don't know anything about the system itself, because of these properties, you could still get the output. Okay? So, do you want me to explain this again? Because again, this is very important.
It's better if you give us an example.
This is the exact example. Okay? I can't be more clear than that.
The times 2 scaling, where did that come from?
The time to scaling is because you can see here, what is the amplitude? 1. What is the amplitude here?
Wait, so are we given?
Are we given?
This is given to you.
Oh, okay.
So the question is this. Let me go back to the question.
Show us how you would word a question based on this.
This is exactly how I would word the question. Okay? So I would give you an input, okay, x of t. And I would tell you for this particular input, the linear time invariant system produces this output. Okay? Then I will tell you now, without knowing anything about this linear time invariant system, I haven't told you anything about it. Okay? So you don't know anything. What is the output when the input changes to this periodic signal? And because of those linear time invariance properties, you can still give me the output without knowing anything about the system itself.
We need to give you like the formula or draw the graph?
Probably it would be very similar to this question. Again, I can't be more clear.
Just write down the whole thing. Just write down
You could use that, but again, the numbers might change, the shapes might change, so unless you understand the concept, you won't be able to solve it.
The numbers are changing.
Yeah.
The shape is changing. Obviously.
Sir, I think I got it.
So are we good?
Yeah.
Should we move on?
Yes.
I hope I was clear enough.
Unbelievable.
Okay, so let's see. Then, okay, so what did we do next? Okay, we introduced the impulse response. So this impulse response is also important, okay? So what was the idea behind the impulse response? When we have a linear time invariant system, if the input is the unit impulse, the output we call impulse response. So if I ask you what is an impulse response, you say it is the output of a linear time invariant system when the input is the unit impulse. Okay? And because of the linear time invariance property, if I scale and I shift these things, I have to scale and shift the unit impulses, the impulse responses. So this is again, these examples are important. If I give you a system and I ask you what is the impulse response, you should be able to tell me, okay? And it's very easy. Wherever you see your x, you substitute your delta function, because the impulse response is the output when the input is the delta function, or the unit impulse. Okay, so these examples, review them. And again, this is another, because I want this idea of linear time invariance to sink in. Okay, this is another example. If I tell you the impulse response is this, okay? The impulse response is when the input is just the delta function. And I tell you now what is the output of that system, okay? What is the output when the input is that sum of those time-shifted versions of impulse response? You simply shift them, you shift the output, you multiply it with your constant, and you add everything up together. Okay, the same concept that you saw going from that non-periodic signal to the periodic version applies here. Okay? H of t is the output when you have unit impulse.
So that's the delta only, right?
Yeah.
So in this case, the 3 delta t minus 2 is...
So 3 delta comes to, so at say the 0 should move to 2. 0 has moved to 2. And also it should scale by 3. It has scaled by 3, right? This middle portion. For the first one, you have to go to the other side, right? So if you were at 0, you should go to -1. If I was at 0, I go to -1. Yeah, you shift and you scale and you add.
Wait.
Same concept. Yes?
Will we have to graph h of t? Like, will we have to know that it looks like that, and then will we have to be...
Oh, no, this is a very specific example. H of t is never like this. I mean, this is just one example, you know.
Okay.
For some system that we don't know, H of t is this. Okay? And then, if I tell you now the input changes to that, you can tell me the output. Okay? Questions?
Yeah, hold on.
Yes?
I'm just trying to understand.
Yes?
If you were to ask this question, you would have to compare this with the initial graph, right?
Yeah, definitely. Definitely. Another thing to remember about the impulse response, it completely characterizes the linear time invariant system. So if I give you the impulse response, you know everything there is to know about the linear time invariant system. Okay?
My question.
Yes.
In here, when you give an h of t and then you're told that the input is x of t,
Yeah.
it's supposed to find the output, right?
Yeah.
So in x of t, wherever it says, or whenever there's a constant in front of the delta, is that like the magnitude?
Yeah.
Okay.
Yeah, it's like the scaling we saw with the from here from 1 to 2. It's the same concept. We multiply the by 2, right? Yes.
Which part of the slide is the impulse response part?
This is the impulse response, right? H of t. H of t is the impulse response, and it's the output of the system when the input is the delta function. Now, if I have an input which is a shifted, scaled version of those, it's gonna be, we're gonna shift them by the same amount. So here, instead of, maybe I should write this.
For like, in the midterm, hoping it won't be this complicated. It's hard to graph.
No. Of course.
You're given the x minus
Yeah, don't worry. Anyways, you're not going to see something complicated. So then we derived the convolution. Okay, and this was the formula for convolution. This was the nasty integral that we had. Okay, and we saw an example. Obviously, you're not going to see an example like this because it's going to take you 30 minutes just to solve it, probably. This you have to know the concept, just the general.
So just know the concept of convolution.
Don't worry too much about convolution, okay? But there's a big but. Okay? The properties of convolution. These are the ones that you're supposed to know. Okay? The properties of convolution These are the ones that I like to know. The general formula for convolution I like you to know. That's all. I don't want you to be able to carry out complex convolution operations, okay? You don't need to do that. But these properties you have to know. You have to know that what is convolution? The convolution is basically used to get the output of a linear time-invariant system for any input x of t. Okay, and the way you get that is using the impulse response. So when you know the impulse response, what you do for any input, you convolve it with your input and it gives you the output. Okay, so convolution gives you the output of a linear time-invariant system. And these properties are important. So these two, very important, okay, because they make the convolution operation easy. Okay, instead of that complex integral, you have a much simpler integral. And here, again, you see the delta function is very special because when you convolve any signal x of t with the shifted version of x of delta function, the output is a shifted version of the signal. So you don't have to carry out any integration. Okay? So if you need to convolve two signals like that, you don't have to carry out any operations. Okay? So tell me, what is the, if I have x of t convolved with delta of t, what is the output?
X of t.
X of t. That's it. Okay? Yeah, this last one is okay, and that's that. Yeah. Okay, let's see number 11. Okay, number 11 is also important. So, for number 11, again, I want you to understand the general concept. Okay? So we talked about convolution, its properties, and then these ones are important. Okay, when we had cascade systems, that means systems of, you could create more complex systems using individual linear time-invariant systems, and you could have systems in parallel like this, or in series. So the general idea is, if you know the impulse response of these individual systems, you could calculate the overall impulse response of this whole system. Okay, and this is how you do it for parallel. You simply add the impulse responses together. Okay, simply add the impulse responses together. In case of series, you convolve the two impulse responses together. Okay, you convolve the two impulse responses together, and that gives you the overall impulse response of the whole system. Okay, and also for series, it doesn't matter if you switch the systems, okay, the order of the systems. Now, this example is important, okay, and the next example is also important. So make sure you know these two. Okay, it's lecture 11, slide 16, and the next, I think, 3 slides that follows. The next 2 slides that follows. So the overall idea is, if I give you a complex system like this, where you have a bunch of individual linear time-invariant systems, and I ask you to give me the overall impulse response of the system. Okay? When you have parallel systems, you add them, and when you have this whole thing, and you have two series, you convolve them like this. Okay? And this next example captures that as well. Okay, so if you have a complex system like this, and I tell you, this time I give you particular values of the impulse response. Okay, because these are in parallel, you add them. So when you add, you have u of t, you have a minus u of t, these two cancel, so the overall impulse response of this system is u of t minus 2. Okay, and then these two, these are in series, so you have to convolve them. When you convolve this one with this one, this is a special case, right? So you could use those properties, and this is the answer you get. Okay, so you convolve those two, you get t minus 2 plus 2, okay? Because there's a plus 2 here, and there's a minus 2 here. And the 2 cancel out, and you get u of t.
That's for the parallel in the series.
So that's for these three. Okay? And then at the very end, when these three come out, these three and this one are again in parallel. So you add them. So you add this u of t, which was the result of this system, to this one. And that's the sum of them. And that would be the overall impulse response of the whole system. Okay? So this one is simple. Okay? Then we said, okay, if we know the impulse response, we already know that the system is linear time invariant, but can we characterize the system as memoryless, causal, and stable? Okay, and we said these are the conditions. If for memoryless, if your impulse response is in the form of some constant c multiplied by the delta function, and notice it's not the shifted version. It's just the delta function it has, exactly.
Could CV1.
So,
Could CV1.
yeah, could be anything. As long as you have that, the system is memoryless. For causal, for causal, I passed it, right? So for causal, if the impulse response is 0 for t is less than 0. Okay? If the impulse response is 0 for t is less than 0, and for stable, this was the condition. So go over these slides, just review these things. And the last one is the invertible system. Okay? And again, this invertible system is also important. Okay? Make sure you go over this example as well. Okay? And the general idea is a linear time invariant system is invertible if there is some inverse system with some impulse response h of it that gives you back the delta function. Okay, because the input is the delta function. For the delta function, you get the output, which is the impulse response. And if you have that inverse system, you get the delta function. Okay? Okay? So if I tell you I passed some signal through a system, okay? This is important. If I tell you I pass signal through a linear time invariant system, okay, and I know the output, okay, but I don't know what the input is. But I know the impulse response of the system, okay. So I know the output, I know the impulse response. I want to know which input it came from. What input generated that output, okay. What I do is I have to calculate this inverse system, and by passing the output of the original one through that system, I get the original input. Okay? So this one is again important. If I tell you the output of a system, okay, you know that. And if you know the system itself, okay, for example, you know it was a multipath system, okay, and you want to know which input generated that output, okay, you have to find an inverse system, okay, and use that inverse system to get the original input. Okay, by passing your output signal through that inverse system, you find the original input. Okay, so go over this example. Go over this example. Okay, this example demonstrates that. You have a system with impulse response h of t. You want to find the inverse system of it. The inverse system of it. Okay, and this is how you find it. Okay. Sorry?
I'm going to fix the square root again.
No. I guess that's it.
Thank you, sir.
Yeah, no problem. There's a lecture 12, but from that, like I said, just review it. There's going to be just maybe 1 or 2 questions in the